My name is Xiaokang from Shanghai Jiao Tong University. The work I'm going to share is QZFS, QAT Accelerated Compression File System for application agnostic and cost-efficient data storage. It was done by the cooperation between our university and Intel. Let's first see the background. High-performance computing provides powerful computing capabilities for handling big data. It involves massive storage I/O read-write operations. So, an important requirement is the performance and efficiency of the storage subsystem. This requirement can be satisfied by NVMe SSDs, which provide remarkable increase of read-write speed with no energy consumption, but it comes with high price at the same time. For example, Intel SSD data center family costs nearly $500 per terabyte. And for Mixture, the HPC system for climate research in Germany, the storage subsystem accounts for roughly 20% of the total cost of ownership. Data compression is an effective solution. It not only achieves space efficiency for lower cost, but may also provide higher performance because of reduced I/O operations. But again, the benefit comes at the expense of CPU resources, leading to the advent of all kinds of compression accelerators for offloading to free up CPU. Data compression could be integrated into different system layers. First, the application layer, which is most common, such as Nginx, Hadoop. Second, the file system layer, which can benefit all applications, such as ZFS, BTRFS. And last, block layer, which achieves file system agnostic. An example is the recently released Red Hat VDO. Our work investigates ASIC-based compression offloading at the file system layer, using Intel QAT technology. It's a modern ASIC for cryptography and compression. Its type include PCIe adapter, chipset, system on chip. The performance of the latest QAT device is up to 100 gigabits per second, and the price is low to $32 after putting to chipset. Since our work is based on ZFS file system, let's have an overview first. ZFS combines the roles of both file system and volume manager. And the pooled storage in ZFS actually eliminates the antique notion of volumes. ZFS provides transactional operation for consistency and provide end-to-end data integrity, RAID, encryption, compression, and so on. It has the concept of record size, which defines the maximum size of a block that can be processed by ZFS. And the default size is 128 kilobytes, and it can be configured by the user. So this kind of record size means the possibility of varied block size for compression. Our work proposes QAT accelerated ZFS, named QZFS, which integrates Intel QAT into ZFS for efficient data compression offloading. We choose to offload gzip algorithm because of its high compression. QZFS is designed to transparently benefit all applications running on it, featured by high performance, high space efficiency, and low CPU utilization. There are two main design considerations. First, the compression-related function needs to be replaced with an I/O core to interact with QAT, but QAT hardware treats data in a different way from the software. Second, considering the offload overhead and the pre-allocated system resources for QAT offloading, we need to investigate the necessity of hardware-software switch or even compression-non-compression switch. This is the QZFS architecture. It can work as either local file system or the backend of the raster distributed file system. The ZIO module is the centralized module where I/O requests are abstracted as ZIOs and forwarded to other modules for processing. The I/O compress module, this is responsible for data compression and decompression. QZFS introduces two new modules, compression service engine and the QAT offloading module. A complete data writing workflow starts with the ZIO module, which forwards the ZIO compress request to ZIO compression module, enter the service engine, and choose a select algorithm from software library or hardware acceleration. For QAT offloading, it sends the compression request to the QAT accelerator, and when it is complete, the response is consumed by the QAT offloading module, and the compressed data are returned to the up modules. And finally, the ZIO module writes the compressed data into NVMe SSDs. For data reading, the workflow for decompression is similar. In compression service engine, there is an algorithm selector which selects compression algorithm from Wang QAT accelerated gzip and some other software implementations. It has a uniform interface, which means it can be easily extended to support other compression accelerators. And once a runtime error is detected in the QAT offloading, the system switches to the software alternative automatically. Hardware-software switch is considered. QZFS selectively offloads ZIO requests between with the size ranging from 4 kilobytes to 1 megabyte. This is because for small source data, the benefits are offset by the offload overhead, including preparing the QAT request, consuming the QAT responses, and PCIe transactions. And the support for big source data requires large pre-allocated kernel memory as intermediate buffers. QZFS also provides compressibility-dependent offloading. We know that no compressibility means that data are not worth being stored in a compressed format, as it will not save much storage space, but incur extra computing resource consumption for later decompression. So if the space saving is less than the 10% threshold, the original uncompressed data is returned to the app applications. In QAT offloading module, we need to consider that the data prepared by ZIO uses virtual memory, but QAT hardware requires contiguous physical memory for DMA operations. So data reconstruction is needed, and our goal is zero memory copy. QZFS uses vector I/O module, also known as scatter-gather buffer list. And QZFS partitions data by page frames into multiple flat buffers. In each flat buffer, the data is physically contiguous. When we creating data structure for the SGL, we need to calculate the number of buffers, and it is calculated by the possible maximum, and the resulting zero buffers are automatically handled by the QAT driver. For address translation to locate physical pages, we need to differentiate different kernel memory regions, including vmalloc region or direct memory region, and we need to use different address translation functions for them. And when a physical page is located, we use kmag function to establish long-lasting mapping. In evaluation, we use a last cluster with varying nodes. In a full load cluster, we use 2 client and 2 object storage servers. In each server, an SSD array and one QAT device were equipped. The QAT device has a hardware limit of 24 gigabits per second. Two benchmarks were used, FIO micro benchmark and genomic data post-processing. We use a cost efficiency metric, which is calculated by the ratio between compression ratio and the CPU utilization. Here, we do not take QAT cost into account, as its price after putting into a chipset is negligible compared to the CPU price. For FIO micro benchmark, there were 16 FIO threads in each client. We first compared software gzip with the QAT accelerated gzip. We can see that for the software gzip, the sequential write and random write, the CPU utilization is up to 95%. This actually have a great impact, an impact on the normal running of FIO benchmark and cause the very low throughput. This is only 1/3 of the case of compression off. After the gzip is offloaded to the QAT accelerator, we can see the cost efficiency is greatly increased, and the real write throughput for the QAT accelerated gzip is even higher than the compression off. This is because the storage I/O operations are reduced because of compression. We also compared QAT accelerated gzip with other fast compression algorithms such as LZ4, and QAT accelerated gzip still achieves the highest cost efficiency, especially for the write operation. For genomic data post-processing, same tools were used to perform file representative operations. And in one client, 8 processes were launched to manipulate 76 gigabits genomic data. We can see that QAT offloading reduces the execution time by 63% and provides 6 times cost efficiency because of the low CPU utilization. We also compared QZFS with simple gzip at application layer to perform a genomic data converting operation. Here, the simple gzip means the application has no compression module, but use the gzip tool for compression. So when the application performs converting operation, it first should go through the decompression process, including read compressed data, decompression, and write uncompressed data back to storage. And when it performs converting process, it read uncompressed data, converting, and write new format back. Here is the QZFS. It achieves the total execution of QZFS is even smaller than the pure converting process of the simple gzip, because QZFS directly rewrite compressed data and perform decompression and converting simultaneously in multiple threads. Actually, it's no doubt that application can achieve similar performance by integrating well-designed compression module, including data fragmentation, compression, multi-thread, and using QAT. But each new application may involve heavy modification. In contrast, our work involves one modification to the ZFS file system, and it can benefit all applications running on it. At last, I want to discuss the bottleneck. For the FIO benchmark, even the highest throughput does not achieve the hardware limit. We can see for the CPU, SSD, NIC, or QAT, they do not achieve the hardware limit. So what is the bottleneck? First, the number of ZFS work threads with offloading ability is limited by the number of QAT instances. And more importantly, a work thread interacts with QAT in a synchronized mode. It means the next compression request cannot be submitted until the completion of the previous one. So in this kind of mode, you can, even if you use more FIO threads, it cannot give rise to the parallel or concurrent QAT requests. An approach to overcome this bottleneck is to use async offload mode. It's typically used when you want to utilize QAT accelerator with limited number of threads, and it has the ability to make one thread can concurrently offload multiple operation tasks. However, the async implementation is not easy. It involves async support in all layers of ZFS software stack to handle and recognize an incomplete task. It needs efficient pause and resumption of an offload job in one work thread. And when you re-enter a CM handler, you need to use state flag or fiber or coroutine. But we do have a reference named QTLS. It implements a high-performance SSL TLS asynchronous offload framework, and it was published in PPOP 2019. So thank you. Is there any question? Our work has been integrated into the QZFS Linux release, and other QAT-related projects are also available on GitHub. Thank you.
Abhinav Gildel, nice work. With QAT, what we've seen is that when it reaches the bandwidth, the latency goes really high. And the side effect is that by implementing this in the file system, the application's performance can really go down because you don't know how much it can really support because you're compressing everything. Have you any thoughts on that, or have you seen such behavior?
Since the compression and decompression are performed at the file system layer, it has the granularity of the block size. The ZFS has a block size of maybe no more than 128 kilobytes. And if you want to read a file or some, the latency is determined by the, I think it's determined by the size of the compressed block.
Okay, so QAT offloading has a latency because you are giving the work to QAT card, and unless you give enough requests, you cannot offset that latency. So that in general has been a problem with QAT. So my question is, have you observed that?
If I offload the compression work to the QAT, yes, the latency will be increased?
Yes.
Actually, the QAT can perform the compression and decompression much faster than the CPU. So in our test, if you offload the block size more than possible 64 or 17 or 80 kilobytes, the QAT can do the compression much faster than the CPU. So even if the request and the response, it's still smaller, takes smaller time than the CPU.
Okay, thanks. Okay. We can discuss offline.
Any more questions?
So Nadav Amit, VMware. So regarding the latency, don't you see any effect of caches as well? Because data needs to traverse from the CPU. Does QAT support DDIO?
DDIO, I think
no. Do you move the data from the CPU to the device as well? So you have the latency of the PCI, for
Yeah.
the DMA,
Yes, yes.
and you also have and you also potentially access the memory. So do
Yeah.
you see any latency because of that? Like for small IOs, do you see an effect? 80 kilobytes is enough for, yes? Okay.
Actually, for small block size, maybe the whole latency when you use QAT is longer than the CPU case. Okay. Yeah, that's true. But in our evaluation, we can see that if you use some high compression ratio algorithm like gzip, the CPU utilization for the software implementation is very high. So it may affect the normal running of the application. So if we can offload the compression task to the QAT, the CPU is freed up to dedicatedly running the application. So the whole system performance can be enhanced.
Okay, let's thank our speaker one more time.